Electrocyclic reactions are one of a larger group of pericyclic reactions defined by those having the cyclic transition state. They must be concerted, and their bond orbitals must overlap in the transition state. Pericyclic reactions include sigmatropic reactions and electrocyclic reactions. Electrocyclic reactions are defined by a pi bond converting to a sigma or vice versa. They can be thermal or photochemical. In fact, all electrocyclic reactions are allowed in some way. They can be ring opening or ring closing. In other words, either the forward or the reverse reaction is possible. And they can be conrotatory or disrotatory. And that defines the stereochemistries of the products. I'd now like to demonstrate my ChemDraw skills by drawing the LUMO of ethene at supernatural speed. I bet you couldn't do that. And how about this for the LUMO of 1,3-butadiene? Fast, huh? The LUMO of 1,3,5-hexatriene takes a little bit of thinking about. If the LUMO of ethene has one pi node and the LUMO of 1,3-butadiene has two, then the LUMO of 1,3,5-hexadiene must have three, and those nodes must be equidistant in the continuous molecular orbital that forms in the transition state. The only way to do that is not have any orbitals on C2 and C5. That gives you three equidistant modes when the two ends of the system are joined. Let's consider a ring opening of cyclobutene. The HOMO in this is the sigma bond. That's filled with electrons. The LUMO is the LUMO of the ethene component. When that sigma bond breaks, to keep the white lobes of the orbitals matched on the HOMO and the LUMO, there has to be a conrotatory motion, like modern windscreen wipers. However, in the ring opening of cyclo 1,3-hexadiene, the HOMO is still the sigma bond, but to match the LUMO, it has to rotate in opposite directions, disrotatory. Think of old-fashioned windscreen wipers, like in Casablanca. Here's looking at you, kid. But if we look at cyclo-octa 1,3,5-triene, ring opening of that has to be conrotatory again. Well, that's really of no consequence unless we have substituents on the cyclobutene. Let's consider two cis methyl groups. If the ring breaks in a conrotatory manner, they either have to turn both to the right or both to the left, and that gives an EZ-diene. However, if we take trans 3,4-dimethyl-cyclobutene, if that opens by a conrotatory thermal process, then the product has to be either EE or ZZ. EE is preferred to prevent steric interactions between the two substituents. If you think you understand this, I'd like you to check by working through the ring opening of substituents on a 1,3-cyclohexadiene system and a 1,3,5-cyclooctatriene system. Remember, the reactions are stereospecific. Only certain geometries of the double bond are allowed. Thank you very much for listening. Goodbye.